All right, hello everyone. Welcome back to today's lecture. Today we're going to talk all about tectonics, which is the movement of plates and continents on the Earth's surface. So first, before we go into how plates move, we first have to know about the structure of the Earth. So the Earth is composed of multiple different layers. The first of which at the surface is the crust. You can kind of think of the crust as kind of the skin of an apple, roughly equal in proportion to that too, and has very different properties from the rest of the planet. So the Earth's crust is composed of two different types of crust. So we have continental crust, which is fairly low density, fairly thick, and is composed of a lot of felsic minerals such as granites. And then there's oceanic crust, which is high density, fairly thin, and has a lot of iron-rich minerals. And you can see here, this is an oceanic crust, and here is a continental crust. And so that crust can form a brittle layer. And so the lithosphere is the layer of which plates actually move. So it's the layer of the upper mantle and the crust that moves brittly along the surface of the Earth. And so you can see here, this is a map showing the thickness of Earth's crust. And the thickest areas, such as in the Himalayas and the Andes, are thick continental crust areas, whereas the thinnest areas, such as in the oceans, are very thin. And you can see here that the thicker areas are tens of kilometers thicker than oceanic crust. The asthenosphere is below the crust, and it, unlike the lithosphere, acts plastically. It can be easily deformed, like this ball of Play-Doh here. And it's what allows the plates to move because it's fairly weak in structure and can deform as the plates move on top of it. And so the bottom of the crust and the top of the mantle is defined by something called the Mohorovics discontinuity, probably pronouncing that incorrectly. It's also just called the MOHO for short. And so the MOHO is a distinct difference in how quickly seismic waves can move through the Earth's material. So through the crust, seismic waves tend to move relatively slowly, whereas in the mantle, the seismic waves can move more quickly. And that difference is the MOHO line. And so below the mantle, that mantle is kind of one of the thicker layers of the Earth, has upper and lower mantle, and deforms somewhat plastically. Below that, we have the core. And so the core, maybe you saw this kind of awful movie, is composed of both the outer core, which is liquid, and the inner core, which is solid. And so the core is pretty much completely composed of iron and nickel metal. And the reason why the inner core is solid is because it's under such great pressure that it's been smushed together hard enough that it's a solid, whereas the outer core doesn't have as much pressure on it, and so it can stay in its liquid form. And it can flow too around the inner core. So next, because of that movement of liquid around the Earth's inner core, and because that outer core is made mainly of iron that's magnetic, you have the Earth producing a magnetic field, and these magnetic fields are very important for keeping out solar winds from our planet. The sun releases a lot of highly ionized particles, and the fact that our Earth produces its own magnetic field means that we're shielded a lot from those ionized particles. So how do these actually form? We're going to watch this video to find out.
So to produce the Earth's magnetic field, you need three things. First, you need a conducting liquid. You need that liquid to be in motion, and not just chaotic motion, but fairly ordered flows. And you get that from two processes. First, convection. So the core of the Earth is extremely hot, and so much like a lava lamp, it cycles through up and down and circulates. But then it gets complicated because it's also rotating because of the rotation of the Earth. And so this sets up some very complicated flow patterns. And then the third really important ingredient you need is a seed magnetic field. So something has to be there to start with. And once you've got that, you have magnetic induction. So you've got a conductive fluid moving across these magnetic field lines in this ordered flow. And when you have a conducting fluid moving across magnetic field lines, you generate electrical currents. Those electrical currents in turn generate magnetic field lines. And so you have this self-perpetuating system.
Yeah, so the Earth is pretty cool and forms its own magnetic field because of the movement of that outer core material.
So
additionally, the location where those magnetic field lines come out of the Earth, also known as the magnetic North Pole, has been moving. And we can see that that movement has been steadily accelerating in the 1600s all the way up into 1850s and the early 1900s. The magnetic North Pole was located in northern Canada and has since been shooting off towards Russia as that magnetic field has been shifting. And that's because the magnetic field is not constant. These are some of the magnetic field lines in a model that was made to try to understand a process called magnetic field reversals. So from the geologic record, we know that every so often in Earth's long history, the magnetic field can go pretty much completely haywire as the fluids that are moving in the outer core change their direction. And when that happens, the North Pole, where you have those magnetic field lines, can completely switch to the South Pole. And this is a simulation of what those field lines would look like in that process. So we have a number of ways of measuring Earth's magnetism and gaining more information about Earth's magnetic field and how it varies throughout our planet. And this is one of the earlier magnetic field measuring devices that was used in the World Wars. And a lot of times we run these types of machines on ships. During the Second World War, for example, we used magnetic field meters on ships in order to try to detect submarines and protect ships that way. And what we saw when we looked at all the data that was coming up from these ships is that the magnetic fields and the strength of those magnetic fields, which is plotted here, form these strange concentric lines. And that the magnetic field seems to reverse in regular patterns parallel to the shape of the Atlantic Ocean. So that was really interesting and puzzling to scientists when they first discovered it. Additionally, these magnetic field reversals that could be seen in the geologic record seem to be matching up with the mid-ocean ridge that was discovered as well, which is the largest ridge in our planet that goes all the way up to the length of the Atlantic Ocean. And so what they saw was that as you move further away from these mid-ocean ridges, then you have these concentric lines of similar magnetic fields. And so you have an area with magnetic polarity that we would see today, and then further away you have that magnetic polarity reversed, and then it has these bands as you go further out. So the reason that this occurs is because magnetic minerals can store the magnetic field that they were exposed to when they formed. Magnetic minerals such as magnetite, it's an iron-rich mineral, has these oriented grains within it, and those grains can move around when it's really high temperature. We call that the Curie temperature at 580 degrees Celsius. And those mineral grains will align with the Earth's magnetic field. And then once that rock cools to below that Curie temperature, then those minerals are set and they can't move around anymore. So they record the ancient magnetic field of the planet. And so we can use that in order to figure out what the magnetic field was millions of years ago. What we see here is that the magnetic fields seem to correlate really well with the age of the rock that each is in. And so as you move further away from the center of the mid-Atlantic ridge and where you have magma coming up, you get older and older. So the youngest rock is located closest to the center of that ridge, and you have bands of magnetic reversals moving away from that ridge. And you can see that here. This is a map of the age of oceanic crust. And as you move further away from that mid-Atlantic ridge, then you get older and older. And so this was kind of puzzling to a lot of scientists at the time to see that there's a new oceanic crust that was being formed. One of the scientists that really got interested in it was a guy named Alfred Wegener. You may have heard of the Alfred Wegener Institute in Germany. He became a very famous scientist. And so he noticed that fossils that he found from South America looked very similar to fossils that were being found in Africa. And it was almost as if the habitats of these extinct animals must have been somehow connected in the past. And so he came up with this map where he thought that the continents must have all been one large landmass before and have since separated apart. A lot of people dismiss this. The main reason for which was that there was no mechanism that he proposed. He didn't know how you could actually move continents. And so a lot of people just didn't believe him at the time. And it wasn't until later that we started gaining even more evidence to support Alfred Wegener's ideas. Personally, I think one of the reasons why he didn't get as much credibility at the time is because he wears, in my opinion, some pretty funky looking hats, but that's my own personal theory per se. So the idea of plate tectonics was born, and the idea states that you have these brittle continents that are moving along the surface of the Earth and can move in relation to each other. And between them, we have plate boundaries that are going around the entire planet. And you can see those here with the different plates moving, such as the North American plate slowly moving to the west, the Nazca plate moving to the east, and so forth. And you have several of these plates throughout the planet. We can measure the speed at which these plates are moving using GPS. So for example, this is a very high resolution GPS that's drilled in place, and it measures its location over a very long period of years. And then we can tell how quickly those plates are moving based off of those GPS measurements. And you can see here these numbers correlate to how fast the plate is moving in millimeters per year. So you have some plates that are moving very quickly, such as these plates over here, whereas other plates, such as Saudi Arabian plate, is moving very slowly. And so that gives us a good idea of how these plates are moving in relation to each other. And we can use that information about how quickly that the plates are moving, as well as some complicated computer models, in order to predict where the plates are going in the future. And so we expect that in around 250 million years, we're going to have another supercontinent where the North American and South American plates combine with the other plates and form another kind of Pangea, which was the previous name for the supercontinent that has since broken apart. So yeah, Pangea was definitely a big deal, and it had big consequences for the geology and life forms that were living there. And actually, before we had the mid-ocean ridge separate, we actually had a big interior seaway in North America before the Rocky Mountains formed. And so, yeah, there's major changes had occurred because of plate tectonics. The reason why these plates move is because of mantle convection. So just like as we talked about in the atmosphere with atmospheric convection, in which the atmosphere can circulate because of differences in temperature, and that can move air around, the same process can happen in the Earth's mantle, where you have the core of the Earth heating up the mantle, and that heat allowing the mantle there to rise, and then once it hits the crust, it separates and comes back down as it's cooled. And so as that convection happens, you have movement of the plates. So the moving mantle material comes up and it pushes up on mid-ocean ridges, and it pushes them apart, but also it drags against the other side of the plate and it pulls them down through a process called slab pull. So that's actually kind of the major process that drives these tectonic plates to move, is they're both being dragged down and pushed apart by this mantle convection current. You can see here, this is an animation of mantle plume development over billions of years, and it's not a simple process, but the basic physics is just saying that as the core heats the mantle, you're going to have that heated material rising and circulating the material. Next, we're going to talk about plate boundaries, because when tectonic plates move, the interesting things happen at those boundary locations where you have plates moving against each other. And that boundary is called a fault. And so there are three different types of plate boundaries. The first one we've already talked about is a divergent plate boundary. This is when you have mantle material coming up and separating two plates apart. And in turn, lava comes up out of this ridge and the new oceanic crust develops. This not always happens in the ocean. It also can happen on land. This is Thorsmork in Iceland, very cool place, where we have a divergent plate boundary on land separating these two continents apart. The other type of plate boundary is a convergent plate boundary. This is when, instead of separating, two plates are colliding with each other. And so the dynamics of how that happens depends on whether these are oceanic plates or continental plates that are hitting each other. And so for ocean to ocean convergent boundaries, you have one plate that sinks below the other plate, and you can have an accretion prism or wedge develop as some of that material gets scraped onto the other plate. And then you have a trench also developing as that plate sinks down and brings drags that material down with it. Because there's a lot of water that's absorbed by this oceanic plate, water makes rocks melt more easily. And so as that water is released, it melts some of the rock as it goes lower and lower and deeper where it's hotter. And so that magma that develops rises and pokes through the surface and forms a volcanic arc. And so you can see this, for example, the Aleutian mountains and volcanoes in Alaska, in the Alaskan Peninsula, are formed through this process where you have the Pacific plate hitting an oceanic plate and forming this long row of volcanoes as that plume comes up. The next type of convergent plate boundary is an ocean to continent plate boundary. Remember that oceanic plates are significantly more dense than continental plates, despite the fact that continental plates are much thicker. And because that increased density, oceanic plates always go below, or subduct is the term for when a plate goes below another plate. And so it subducts below the continental plate. And you still have that water driving melting and plumes rising up. But instead of a volcanic island arc, you have a continental arc develop. And so we see that an example of that in Northwest United States, the Pacific Northwest, where we have mountains such as Mount Shasta and Mount Rainier, Mount Hood, that form this line of tall volcanoes all along the coastline where that plume comes up. This particular volcanic arc is formed by the Cascadia Trench, So the Juan de Fuca plate, which is the smallest plate in the world, is subducting below the North American plate. And very soon, this whole entire plate will be, or I guess soon in terms of geologic time, millions of years, this plate will be completely subducted down underneath the North American plate and will melt away and be replaced with newer Pacific plate. So then the last type of convergent plate boundaries is a continent-to-continent plate boundary. And so these are very thick plates that have relatively equal densities. And so when they hit each other, they collide, and they don't really know which one should subduct under the other. And so you have a lot of mountain building that occurs. These plates smush together, and that compression causes mountains to build up. And so usually some of the tallest mountains in the world were formed by continent-to-continent collisions. The most famous of which are the Himalayas. Mount Everest, for example, was caused by the Indian continental plate smashing into the Asian continental plate and forming very large mountains as a result of that compression. Then the last type of plate boundary is called a transform boundary. And this is when two plates are sliding past each other. A good example of this is the San Andreas Fault in California, which you can see here, where the Pacific plate and the North American plate are sliding past each other. That San Andreas Fault goes all the way past San Francisco through Point Reyes, which is in northern Bay Area near where I grew up. And Point Reyes, therefore, has rocks that look way different than the rocks that are just across Tomales Bay here, because the rock that's in Point Reyes, this peninsula here, actually has been moved all the way up from Los Angeles due to that plate boundary moving up along the coast of North America. Additionally, you have a lot of transform boundaries at mid-Atlantic, mid-ocean ridges as well. And so these ridges don't really spread apart in nice even lines. They tend to be in shorter segments, and between those segments you can have transform boundaries as well, at least on the smaller scale. And because of that, you have a lot of earthquakes as well. So even though you have these plates that are moving apart, and therefore you wouldn't expect there to be a lot of collisions and stresses develop, you still have a lot of earthquakes that still develop along the mid-Atlantic ridge, for example, and many of these plate boundaries that are divergent because of those transform faults forming. And so the more stress that develops between these plates, the stronger the earthquake. And you can see here some of the strongest earthquakes in South America and in East Asia. So we can see how quickly that these plates are moving past each other. This is the San Andreas Fault near Los Angeles, and it's moving at a fairly quick rate of 33 millimeters per year past the North American plate. Also, it's important to realize that these plate boundaries are not single lines. So the San Andreas Fault is the line at which the majority of that stress is relieved, and where you have a good amount of sliding past each other. but that plate boundary is much wider, and some of that strain is taken up by cracks that faults that run parallel to the San Andreas Fault. For example, the Eastern California shear zone accommodates about 22 millimeters per year, where you have some of these auxiliary faults also deforming, and not all the deformation occurring at that San Andreas fault boundary. And so the end result is that you have a relatively wide plate boundary, where you have a speed of that plate faster than just the fault itself. So let's talk about faults themselves. So there's a number of different faults. So normal, reverse, and transverse faults. And I guess I'm your own fault. But so faults are just planar surfaces where two rock units are shearing past each other. And so a plate boundary, for example, is composed of the San Andreas fault in that instance, as well as several other faults that are parallel to it. So a fault is just that one line where two rocks are moving past each other along a plane. For example, you can see this very small fault here that's moving through this rock and causing this layer here to be moving up relative to this layer here. And so the three different types of faults are normal faults, reverse or thrust faults, and strike-slip faults. And so this is a normal fault, and we define it by how it's moving in relation to that plane surface. So you can see here that this fault plane is tilted at an angle. And when that layer that's on top of that surface is moving downwards, we call this the hanging wall because it's hanging on top of the other wall, the foot wall. And when that hanging wall is falling, then we call that a normal fault because it's kind of falling with gravity downwards. And normal faults usually develop when you have extension, when you have the area that's under tension and being pulled apart, because normal faults make the landscape longer because they're moving apart. And so the important thing to know is that the hanging wall here that's on the upper side of that fault slope is moving downwards. A reverse fault or a thrust fault is the opposite. So a reverse fault is just when that hanging wall here, the wall that's on top of that plane between the two layers, moves upward. And so you have this layer here that gets pushed upwards due to compression of the rock. You can see these arrows here indicating that this rock is being pushed together, and therefore this hanging wall is being moved upwards, and the foot wall is moving downwards. So we call it a reverse fault when that angle tends to be fairly steep, and a thrust fault when that angle is fairly shallow. And so normal faults and reverse faults are kind of the opposites of each other. And then there's strike-slip faults. Just like transform plate boundaries where you have two different rock units moving, sliding past each other. So a strike-slip fault is just the singular line where that happens, the shear plane where two rock masses are sliding past each other, like you see here. And so there's two different types of strike-slip faults. So there we can describe a strike-slip fault as it shears past each other based off of which direction those two rock units are moving relative to one another. So you can see here, if, for example, this shear plane was flat and you were looking at this upper unit, this upper one is moving to the right, and we call that a right-handed shear, and that's called a dextral shear, because that upper layer is moving to the right, and that lower layer is moving to the left, relative to each other. A sinistral strike-slip fault is the opposite. So that upper layer is moving to the left, and the lower layer, if you're looking at it from a top-down view, is moving to the right. I like to think of it as they're kind of rotating with each other, and sinistral is because it's moving counterclockwise. So counter is sinister. That's the Latin origin of it. So you can see here, this is a sinistral strike-slip fault where you have this rock layer here that's been displaced due to this fault, and this layer here has been moved over to the left relative to this rock layer here. Normal faults can form some interesting topography as well. So when you have an area that's experiencing extension, when that landscape is getting pulled apart, you have a lot of normal faults develop. And you can see those normal faults here where the hanging wall is moving down relative to the foot wall. And so in turn, that creates a landscape of a series of ridges and valleys as the hanging wall moves down and forms a valley, and that foot wall moves up relative to the hanging wall and forms a ridge. So those ridges formed from normal faults are called horsts, and the valleys are called grabens. And we can see that in several different locations. Here, for example, is this would be a graben that's developing where these rocks are being pulled apart, and this layer here is moving down relative to these other layers here. Another really cool place that this happens a lot, and you can see it really easily, is Canyonlands National Park, which you can see here, where you have this area of higher topography, which is the horst, and this area of a valley with lower topography, that's the graben. And these two rock layers are being pulled apart from each other. We can also form some interesting topography whenever we have a linear fault that's strike-slipping past each other, because that fault tends to produce a lot of broken apart rock and can open up pore spaces. Groundwater tends to flow fairly easily through a fault, and so you can have a spring develop as well as pooling of water for what's called a sag pond. If there's any vertical movement to that fault, you might get a scarp, which is just a vertical wall along that movement plane. And you can get an offset stream, such as this one, where you have the water coming in, that fault displacing it, and then it continuing in a different location. And we can see that here as well, where you have this stream coming in, it's hitting this dextral fault, strike-slip fault, and then it's getting displaced into this new location here. So next, we're going to be talking all about hotspots. But first, let's take a break, and I'll see you guys on part 2 of the lecture.